Hello students, in this video we'll discuss arc length and area for polar curves. So given a polar curve, r equals f of theta, for theta between alpha and beta, that's a polar curve, right? So in other words, we can plot this in the xy space, and we'll get some sort of curve like this. That's r equals f of theta. And so as I give you different values of theta, so for example, this might be the value alpha, that's the first angle I see over here, and this might be the terminal angle over here, beta. So everything in this polar curve happens for an angle between an angle of alpha and an angle of beta. So that's what polar curves look like. You start at alpha, and then you draw the ray, theta equals alpha, and then the curve will begin, and then you stop when theta is equal to beta. That's the range of theta, okay? And so I have two questions to ask. I'd like to ask, what is the area that this underneath this polar curve between that and the polar axis, and what is the arc length of this thing? So let's recall that the length of arc of a curve is just the integral from a to b of dx dt squared plus dy dt squared, square rooted dt. Well, now what is x and what is y in polar coordinates? In polar coordinates, what do we have? We have that x is r cosine theta, x is r cosine theta, and y is r sine theta. So let's do the derivative of x with respect to t and see what we're going to get over here. So in other words, what do we know? We know that r is f of theta, so x is really what? So these equations turn into what? They turn into x is equal to f of theta cosine theta, and y is equal to f of theta sine of theta. So those are the equations for x and y. So let's do the derivative of x. So now x, I can treat my theta is really like my t variable here. That's my parameter of the problem, theta, right? And so now I'm going to do dx d theta, dy d theta, right? So what will the length of arc be? So the length of arc is going to be the integral from alpha to beta. And then I have dx dt. So let's do the product rule on dx dt. What will that be? That'll be f of theta times negative sine of theta plus f prime of theta cosine of theta. I'm going to have to square this. That's my f, x prime. What's my y prime? It's going to be f of theta times cosine of theta, and then plus f prime of theta sine of theta squared. And then all that's underneath the what? All that's underneath the square root d theta, right? And so now what we're going to do is we're going to make an observation over here. When I square this term and square this term and add them together, what will happen? I'll have an f squared sine squared and an f squared cosine squared. So the first terms I'm going to get in my foiling out on this expression, this first expression over here, and this first expression over here will simplify to f of theta squared. So L is going to be the integral from alpha to beta square root. What will we get? We'll get an f of theta squared from this term over here and this term over here when I square them. And what will happen over here in the cross terms? Well, what will a cross term look like? A cross term will look like an f prime of theta, cosine theta, f of theta, negative sine of theta times 2. And the cross terms over here will be an f of theta, cosine of theta, f prime of theta, sine of theta times 2. So those terms are going to be equal and opposite due to this negative sign. So the middle terms, the terms when you FOIL have a factor of 2 from the inner and the outer, are going to cancel out. And then we'll have this term squared plus this term squared. So what will that represent? That's going to represent f prime of theta squared, sine squared plus cosine squared. That's going to give you 1. So if you FOIL all this out and cancel the terms and then use the fact that sine squared plus cosine squared is equal to 1, you get this expression over here for the length of arc. And oftentimes it's written like this to simplify it as the integral from alpha to beta of the square root of, well, what is f of theta? F of theta is equal to r, so you write r squared plus dr d theta, quantity squared d theta, and this will give us the arc length of that polar curve. I take the function f of theta, square it, take the derivative of f of theta, square that, add those together, square root, integrate, and you get the arc length. That's stemming from the what? That's stemming from the original arc length formula. Now I'd like to find the area between the polar curve and the polar axis, and so how will I do that? I'd like to find the area, so we recall the following fact. If I have a circle of radius r, that's my radius r. And if I sweep out a sector with an angle of theta, Then what do I know? I know that the ratio of theta over 2 pi r, which is the overall circumference of this circle, and of course that's going to be theta times the arc length over there is going to be theta times r, right? That's the arc length. So in other words, this is the whole circumference, and theta times r is this arc length over here of that sector. Has to be the ratio of the sector area over the total area, pi r squared. So we can cancel out the pi. There's no r over here. And so what does that say? That says that the sector area is just going to be what? It's just going to be theta over 2 r squared. And now what I can do is the following. I can take this polar curve and I can chop up a whole bunch of little small angle differentials, right? So the angle of a small sector like this, if I have a delta theta over here, so the area of a small sector, will be what? The area of that small sector is going to be 1/2. Then we're going to have the delta theta for the change in theta. So let's call that like a theta, maybe like a theta I minus theta I minus 1. If I have a theta 1 angle, a theta 2 angle, theta 3, if I partition the angles theta, if I have a theta 0 equals alpha less than theta 1 less than theta 2 all the way up to theta n, which is beta. So if I partition that sector between alpha and beta with n sort of small angles, and then what? And then times f of what? The function of theta I squared, right? In other words, that's the square, that's my radius is in terms of f of theta. So if I add up all these things, that tells us what? This will tell us that the area, so hence the area between the polar axis and that sector is going to be what? If I'm going to have a Riemann sum looks like this. It's going to be a 1/2 is approximately 1/2 the sum j goes from 1 to n of what? Of f of theta j quantity squared times, that's a j, not an I, of course, theta j minus 1. And as n goes to infinity, as the partition size gets infinitely small, right, this will turn into what? This is going to turn into the 1/2, the integral from alpha to beta of f of theta squared d theta. So this is how you compute the area between the polar axis and the polar curve, and this is how you compute the arc length of that section of the polar curve. Thank you very much.